And since it's recording
Meeting is being recorded.
and allow me to formally introduce the speaker for today, Dr. Han Tu. Dr. Han Tu got his a PhD degree from a mechanical and aerospace engineering. He worked with a Dr. Melissa Green during his PhD, focusing on the unsteady flow around the non-slender delta wings with accelerations. Right now, he's a postdoc research working with Dr. Gao Qi at Zhejiang University. He's currently researching at the evolution of the wake structure behind the hemisphere and the coherent structure generated by fish swimming. So today, Dr. Gauchi is going to talk about experimental investigation of zebrafish swimming using PIV. And Dr. Hantu, this is yours. The floor is yours.
Okay. Okay. Can you hear me?
I can hear you clear.
Okay. Thanks for the introduction, and I'm very glad to have this opportunity to share some recent results that we have done for the research of the zebrafish swimming. And in fact, I was planning to share some important phenomenon we found for the helping vortex induced by a hemisphere ramp immersed in a laminar boundary layer. But at the last, I switched back to this topic. Today's topic, the experimental investigation of zebrafish swimming using PIV, because I think this topic is more relevant to the major concern of this seminar, which is the bio-inspired mechanics. And before the start, I would like to say, so we are still working on this project, and many of those results are just at the middle age. So I just want to share some of those interesting things that I feel that they are maybe cause you guys the attention, and maybe you can so which means you can also give some feedback, and then we can to see how to improve the current work. Okay, so so here comes the first question. So why do we study the fish swimming? Because we think that for those fishes, they could swim in efficient patterns since they are selected by the nature for millions of years. And another very important fact is that we do observe those fishes. They have the ability to continuously react to the surrounding unsteady flow, which is not easy for those man-made underwater vehicles. And another important thing is that we observe the agility for those fishes. So for example, when they faced with predators or other dangers, they can accelerate or start themselves very, very fast or make C-turns in a incredible short time. So that's why we want to study them, since the study, I think it can in turn contribute to the design of the future underwater vehicles. And so there are thousands of fishes. How do we classify them? So basically, I think they are classified depending on which part of the body is used for the propulsion. So the first type is the BCF, which means the fish. This kind of fishes they use their body or caudal fin for the propulsion, and as you can see here, and another type is the MPF, which means they use the median or pair fin for the propulsion. And I think this classification of the swimming type is very well known, especially for the audience here. I just give a brief introduction here for people who may not be very familiar with. And next page. So now let us focus on the BCF swimmers, since they occupy a majority of those fish species, and their motion pattern is quite typical. So in fact, this kind of pattern can be further divided into several modes from, the Agoulian form to the Sonic form. And from the left to right, the body undulations, they are further confined close to the caudal fin or to the tail, especially for the right two, these two kinds. The thrust is provided by a relatively, so-called stiff cattle fin. And in this case, the study of flapping foils or flapping pigeon panels can contribute a lot to the understanding of the kinematics and dynamics of the fish swimming. So, for example, the Melissa's group has conducted many experiments to reveal 3D vortex structures and other very important coherent structures in the scenario of the pigeon panels. So from the best knowledge of mine, I think there are at least two main branches of the study of the pigeon panels. The first one is the selection of the optimal Stillhole number. It is well known that the optimal range of Stillhole number is from 0.25 to 0.35. And in this range, the fish can cruise with a high efficiency. And here, I'd like to cite the work of Melissa Group, not only because I was her student, but also because the group have done many nice work here. So King et al. At 2018, they reported the phase average wake structures at different Stillhole numbers from left to side with an increasing Stillhole number. And it is interesting to see the wake seem to squeeze to the middle plane here, and those structures, they are less coherent at a higher Stillhole number. So I think from point of view of the flow structure, the less coherency may be the potential reason for the less efficiency at a higher Stillhole number for the fish swimming. And another branch is the selection of the cattle fin shape. So by changing the concave angle of the trailing edge, we can get the normal one, the concave one, and the convex one. And the shared vortices in the wake should have different patterns of the organizations. And but the overall wake and of course there are other interesting researches, for example, to understanding the wake effect on the wake, to understand the body effects on the wake, because the body itself will act as a fairing for the cattle fin. So Brooks and Green in 2019, they compared wake structures with and without the body, without the robotic fish body. So okay, so now this is the page that talks about the motivation of our study. This is also a difficult but very important page for this work, since here I will try to make it clear that why we study a live fish swimming. So as we can see, there are a number of parametric studies have been done, and in fact, many of them, they are very well designed based on those robotic cattle fin or pigeon panels or robotic fishes. And those experiments are aimed to looking for optimal parameters or proving that fishes are using those optimal parameters during their lives, since the nature selection or the evolution tells them to do so. But the one thing difficult to duplicate on the robotic cattle fin or robotic fish experiments is the stiffness of the real fish, because fishes, they are soft, but they're not hard. So it is not easy to solve this issue in robotic experiments. And also we notice that the rapid turning manual is rarely achieved by using a robotic fish. So then we start to think, what if we directly observe a live fish swimming? So if we do so, the first two issues, the stiffness of the cattle fin and the body effects those two are inherently solved. And I think by properly designing the experiments, we are able to observe cruise and the seasonal manuals of the live fish. And I must claim that I must insist that there have been many important previous researches about Zebrafish, and there are a lot of milestones. So in this talk, I will try to present some instantaneous 3D wake structures of the Zebrafish recorded by Tomo PIV. So such technique is much less used in the Zebrafish study. And I will try to share some interesting results and share some general vortex related findings during the C-term manual using planar PIV. Okay. So here is our setup for the Tomo PIV. So our observation object is a adult zebrafish. So zebrafish widely appear in those bio-inspired experiments, and because they are easy to maintain, and it should be known that those fishes, they are BCF swimmers, and specifically, actually, they are caraginiform swimmers. And the tested one has a body length of 38 millimeters. So to observe the fish cruising, we built a long tunnel with dimension of 800 millimeters by 80 millimeters by 60 millimeters. And on the left side here, we put a water pump to generate a free stream of 27 millimeters per second, which is not very strong. So the tested fish will be faced with a water current, and it may want to cruise against the incoming free stream. In fact, the total setup basically follows the setup in Morpho et al. In 2017 here. And they also built a swim tunnel for the zebrafish and conducted planar PIV experiments. So here we updated this setup and we launched the Tomo PIV, and the recording frequency of the system is 500 Hertz, which is quite high, and the data is the time resolved. So this is very important because the lasting time for any manual of the zebrafish is very short. So actually, when we conducted the Tomo PIV experiments, we found that it is not easy to obtain clear shots of sea terms, since the fish was prefer to cruise if there exists any free stream. So we also conducted the planar PIV in a water tank without any free stream. So in this case, the tested fish has a larger possibility or willing to make sea turns. So the experiment setup follows the setup of Ting and Yang in 2009, and they further applied POD into the wake analysis of the fish. So in our study, we applied FTLE, which is a Lagrangian method, into the wake analysis, and the application of FTLE to the zebrafish wake is rarely done before. So by the way, the recording frequency for the planar PIV is also 500 Hertz, which is quite important for the integral calculation of the FTLE. So that is the experiment setup for our two kinds of PIV system. And so now we are stepping into the results part. So first, I'm going to show some instantaneous 3D wakes of the cruising zebrafish. So if you do experiments with zebrafish, and you will know that it is very hard to let the fishes do what you want them to do. So here we show one good typical case of the cruise, and the green shape here is the cattle we use the technique called SFM, which is the structure from motion, to reconstruct the fish tail. And the orange and the red lines, they are trajectories of upper and lower tips of the cattle fin. So by tracking those trajectories, we can infer the beating frequency of the fish and further calculate the corresponding Reynolds number. So here the beating frequency is 0.3 Hertz, which is a little bit higher than the optimal range, but it's very close to the observation of Ralph et al. In 2017, since we have very similar experimental setup and conditions. And the cruising speed here is of the fish is the 0.2 body length per second against the free stream. So the corresponding Reynolds number is 4185. And we could notice from the fin tip trajectories that the fish cruised approximately along the x-axis. It does not swim exactly along the axis because it is alive. It is not a robot. And then we use the blue isosurfaces of number CI to visualize the vertices in the wake. And here we can see at this moment, so there's water ring VR1 is formed first, and then the cattle fin sweeps to the right. The VR2 began to form, and then the fin sweeps back. The VR2 is totally formed, and VR3 will be VR3 will be generated, and so on. So VR1, VR2, and another vertices together consists of the chain of the linked vortex rings. So such structure is formed by the sweeping, or say the oscillation of the cattle fin, which is clearly revealed from the Tomo PIV experiments and the SFM technique. Another thing is that the high unsteadiness is expected in the wake, since those rings cannot persist for their shapes for a relatively long time. So although those downstream structures gradually lose their shapes, or say gradually lose their coherence, it is still clear that those structures we observe they agree with the phase average results from previous data. Like when we compare here to here, the result from Amarula and Mastuch in 2013, and our instantaneous results of the liverfish also supports the schematic proposed by King et al. In 2018. They proposed this schematic by investigating the wake structures of a pigeon panel. Of course, the work from Melissa's group. And then we pick the third one here for a more detailed demonstration of the cruise wake. So at this time, the vortex ring VR2 is just shed from the cattle fin, and the coherent structure of the linked vortex rings is clearest. So we add the projections of flow on a vertical plane here and a horizontal plane here. So for a better visualization of this structure. And according to those in-plane velocity vectors, we can see the flow seems to converge at the join of these linked vortex rings and present high streamwise, the arrow here, and a high spanwise arrow here through those rings. So if we further zoom in the horizontal plane, there are in-plane strong rotations with alternate rotating directions indicated by those yellow and blue contours here. So for brevity, we name them as vertices V1, V2, and V3. And those vertices form the reverse von Karman street and present a 2S pattern from the two-dimensional point of view. So again, we compare our results with the observation of Marvel et al. In 2017, since the two experiments are very similar. And as you can see, so our 3D instantaneous results is very similar to their 2D wakes, especially in the dotted black rectangular region. So of course, since our experiment was Tomo PIV, so our observation, our data has one more dimension. So it is easy to see that V1 and V2 actually belong to the vortex ring VR1. V2 and V3 belong to another vortex ring of VR2. So except the comparison of 2D and 3D Leaf-Fish results, I think it is also interesting the flow structures of Leaf-Fish and pitching panels. But first, I need to shift the coordinate a little bit to make the new x-axis along the fish cruise direction, since the fish was not exactly swimming along the x direction of the lab frame. So under the new coordinate system, a jet across the rings can be clearly seen. We use the red isosurface to highlight this region. So this one is the isosurface of large U prime. So the U prime means the high velocity in x direction, in x prime direction under the new system. So this region is and the shape. So this region has a shape of as a relatively cylinder bar. On the right here, so this shows the time average wake structures of different pitching panels from Justin's dissertation. So our results is more similar to the concave one here, the most left one, and for the normal one, like the two on the right, the two on the right, for the normal one, the jet region is wider. I mean, the right isosurfaces, they distribute along the trailing edge. And if we see from the phase average results, we can see the difference more clearly, because the from the phase average results, the high speed region, they are vertically placed, while our results, remember our results is the time instantaneous results. So our results show the cylinder high speed region streamwidely placed. So I think this page clearly show the cutoffing effect of the wake structures. And I must note that the first row on the right, their results at the Strickland number of 0.2, while our results of the Leaf-Fish is the Strickland number at 0.45. But if we compare at the same Strickland number, the wakes of the Leaf-Fish and the pitch panel is really different. So I think this shows the stiffness of the cutoffing effect. So for soft cutoffing, it would curve when it push forward and back. So the effect angle of attack and the trailing edge is different to that of the rigid pitching panels. And we also investigate the distribution of the acceleration components in the streamwise and the spanwise directions. So on the top left is the component is the isosurface of the AX, which means the acceleration component in the X direction or in the streamwise direction. So this acceleration is used to overcome the swimming drag, and down here is the isosurface of the AY, which is the acceleration in the spanwise direction, which is believed to support the oscillation motions of the fish. And by the way, the red means positive and the blue means negative. So, and also those isosurfaces they have the same threshold. So at the first glance, the acceleration effect in the spanwise direction is much stronger than the streamwise one, because the corresponding isosurfaces AY, they're much bigger here. And then we propose this schematic. The chain is linked by those vortex rings, and the jets course through them. So the effects of jets should act on both streamwise and spanwise directions. The interesting fact is maintaining the oscillation motion would be more energy consuming than overcome the drag for fish swimming. And similarly, Bayer et al. In 2014, they conducted a CFD simulation and found that those fish spend most of the power to generate motion in the literal, and spends little power to move in the another direction of swimming. Now we also collect some data of turning maneuver in the swimming tunnel, but those data are still under processing. So this page, the title of this page is the 3D wake of sea turn is still under construction. But for the preliminary results here, we can see those vortex rings that one side oriented, as well as those jets, which is very similar to the previous observation done by Sakakibara et al. In 2004. They use a stereo PIV to get these results. So briefly, the fish can manage the orientations of vortices for different maneuvers. Okay, so since those three-dimensional part is still under construction, let us look at the 2D results of turning first. So as we mentioned, the 2D results are conducted using planar PIV, and the fish was freely swimming in a water tank without any free swim. So I make a GIF here on the corner. So the fish is making a left turn right now, and we select several typical frames to study the turning details. So the left figure here gives the snapshot of velocity vectors and the frame and the vorticity distributions. The green contour is the fish itself, and the void of this velocity data is due to the shadow in the experiment, because the laser light comes from left to right. So here is the shadow. And at this moment, the fish is curved into S shape, and the kettle fin reaches maximum amplitude for this left turn. So V1, a vortex, is about to be shed from the kettle fin, and the bending of the fin body should lead to the formation of two bound vortices. We named them as BV1, BV2, and those two, they have opposite rotating directions. So due to the shadow in this data, we cannot see BV1 here, but the BV2 is clear, is indicated by the blue contours of negative vorticity. We also, on the right, we also extract coherent structures of the wake using FTLE. So here the red lines is the NFTLE ridges, which indicates attracting material lines, and the blue one is the positive FTLE ridges, which means the repelling material lines. Okay. So we also use the Q criterion to find the vortex center by using the maximum value of the Q, and so here we can see the feeding shear layer of V1, because here is a red region here, and there is a saddle point S1 marked by the hollow red circle, which separates. So this saddle point separates V1 and the bound vortex V2, and from the aerodynamic point of view, the attached V1 increases the circulation around the fish body. However, the circulation increases towards clockwise, so which is opposite to the fish turning direction. So the fish requires a shedding of V1 for the left turn, and the saddle S1 is expected to depart from the cutoff-in tip. And if we go to the next snapshot, here the cutoff-in reaches its maximum amplitude and starts to pitch back. And at this moment, the fish body is now performs a typical C shape. The BV2 finally evolves into another vortex V2. So as we can see from previous slides, V1 and V2 actually form into a vortex ring or vortex pair. Of course, there is a side jet J1 curls through the vortex pair, and J1 is expected to provide angular momentum for this turning. Now switch to the right side, the Lagrangian perspective. So the saddle S1 moves here, so it travels further downstream along the FTLE rigid. And V1 is fully shared from the cutoff fin, and V2, but V2 is still attached to the fin, and it grows in its magnitude. So we also give an insert figure here to show the U component distribution near the fin tip here, and the white contours represent the negative U component, which means there is a weak thrust effect pointing from the right to the left, even though the fish is doing a left turn. And at the next snapshot, and we can see here another, so saddle, one more saddle S2 can be seen at the fin tip, which implies the shedding of V2 here. And here is also a counterplot of the U component here. So since there are more bright contours, which means a region of high, backward momentum with a high magnitude is expected. So this is totally different from the previous page, that the high the U component is only appear near the fin. So at this moment, there is a high velocity in the x direction, and so the jet along the negative x direction is appearing. The emerge of this jet is consistent with the formation and shedding of the saddle S2. So such coincidence is also observed by Kuma et al. In 2019 on a pitching panel. So here they also observed the such thing happens, agrees with the involution of the saddle S2. And if we go back to several pages here, in fact the jet V1, the side jet J1 is also consistent with the involution or shedding of the saddle point S1. So what I'm trying to say here is the generation of thrust either point to backwards or sideways is highly synced to the motion of saddles, which means the saddles is a nice indicator of the flow involution in the wake. And we also reconstruct the pressure distribution near the fin from the velocity field data. Of course, so this low pressure here is the vortex V2, and there's another low pressure region here on the concave side of the bending shape. So in fact, it is the V3. So the V3 is hiding here. We didn't see the V3 in previous slides because of the shadow here, and the existence of V3 increases the circulation around the fish body in the direction of the rapid turning. So I think V3 is expected to be beneficial for the turning maneuver. And we also expect that the fish should suffer a force pointing to the top right, I mean from here to here, because the low pressure is here and the high pressure is here. So the force should be beneficial to the turning maneuver as well. Okay. And in the beginning, we thought the existence of V3 is just an accident, or even caused by the noise in our data. But then we checked many other cases and found that it is not. So at least for the zebrafish, the wake of turning is composed of a pair of vortices and a single near-body vortex. So the paradigm is, we call it P plus S, which means a pair of vortices here and a single vortex near the the bend body shape, fish body. And so finally, at the end of the turning, the fish is back to a straight shape. The FTI ridges becomes a mushroom shape here. It's very funny. And the mushroom shape keeps on stretching because of the side jet J1. The flow goes here to here. And if we draw the axis AB of this mushroom structure, we can see the line AB is approximately vertical to the fish body. So which means I think the body being perpendicular to the side jet implies that the fish would make the most use of momentum generated by the side vortex pair for the turning maneuver. So I think this figure is a direct presentation of strategy of fish learned from the natural selection or the evolution. Okay, and we also adopt the definition from Rava and Wall in 2017 to use the caudal fin pitching amplitude A and the turning degree theta to describe the turning maneuver. So for the present case, the amplitude A increases first and then goes back to 0 since the fish body was back to straight at the end of this turning. And then we can also estimate the average angular speed of the turning and further estimate the angular momentum for this turn. On the other side, the momentum of the vortex pair can be estimated by this formula. So this momentum is perpendicular, is proportional to the strength of the vortex. And no surprise, the angular momentum required for the turning maneuver is conserved by the vortices in the wake, and because the estimations of L and M, they are close to each other. So the point here is the strength of the vortices in the wake could reflect the intensity of the fish maneuver. And we are going to conduct a more similar quantitative study in the future. Okay. So the summary and the future work. So we used Tomo PIV to observe instantaneous 3D wake structures of a live fish and compare those results to previous non-instantaneous results like time average and phase average. So the overall wake structures, they are similar, but there still exists some significant differences. And we also use planar PIV and FTIE to study the evolution of the coherent structures during a C-turn maneuver. We found that the orientation and the strength of vortices in the wake can very well reflect the motion pattern or condition of the fish. So in the future, we'll conduct a more relevant quantitative study to prove this. And of course, we will finish the 3D C-turn data processing. And that's all slides, and thanks for watching.
Thanks, Dr. Han for this clear discussion. And so we have 10-15 minutes for open discussion. So does anybody have some question? If you do, please just unmute yourself and speak, or you can leave a question in the chat box, and I can communication with Dr. Han. Any questions?
There's a message.
So I guess so the question is from Gongfang Yuan Yu. So thank you very much for your wonderful speech. Is there a mature dynamic model for robotic fish motion control?
Okay, thanks for the question. I think there would be, but so to be honest, first I don't have the exact answer for this, but I know some students in this group they use some cosine or sine function to control the panel pitching or even the part of the body motion. And I recall that most of papers for those pitching panels, they use such function to control their machines. The only thing is, I think they will change their phase or they change their frequency. Also, I think another point is I think people want to find a good ideal numbers in those functions to get a nice or a high efficient for their machines. So I would say yes or no. There is maybe a major one, but we're still looking for it. So that's my understanding of this question.
Okay, thanks for Dr. Hansu's question. Any more questions? Well, I think maybe more question comes, but allow me to maybe throw out some more basic ones and also more a scientific ones like I have. So to begin with, for doing PIV with live fish is always challenging. I know several of my friends who's doing this. One of my close friends doing this an arching fish jumping out of water. And it's not only the technical of the PIV and the tomo PIV, but also into working with the live fish, because they're not always doing what you want to do, and they may be so how you is there any tricks to working with live fish, for example zebrafish you work with? That's the first question. The follow-up question is, if I understand correctly, right now you are in more steady water, in still water for these things. So I think there's maybe more interesting more interesting problems, and of course more complicated ones, is that fish that are in the unsteady wake, whether it's coming from this shading vortex from another fish, basically multiple fish, that may be even more difficult, or shading vortex from a running current, with in the wake of a cylinder, or other say a puffing of a vortex ring from a jet. So from your perspective, if we want to do such experiment, basically manipulate the fish using another wake generator, how difficult this may be, and what insight you may get from that, so from the tomo PIV and the PIV, regular PIV.
Okay, thanks for the question. So the first one, so I think there are two things that we can do is, so before the experiments, we just stop the feeding for a while to let the fish to be hungry, and so because they want to eat, so we can use some food to seduce them, swim into the area we want them to do. This is the first solution, and another one is a more stupid one. We just watch and select and do the recording, and we record a bunch of data cases, and then we go back to the sit down with the computer and do select those good ones, and which means the fish is in the measuring domain, and the vortices are very well shaped. So these are two ways to conduct this one. And some people try to use the laser pen to play with them, but they are not dogs or they are not cats. So they have very limited, at least for the zebrafish, they have very limited reaction to those lights. So I think feeding is a good way to do. So for the second question, that reminds me an old seminar at APS, I remember. So they studied the how to use the tip vortex generated by the front airplane. So so in fact we conducted some unsteady cases experiments. We put a cylinder in the upstream, and we watch the reaction of those fishes in the downstream. but the experiment was not done, or I would say it's not very well conducted because our free stream was too high. So the downstream is more turbulent, and so I think the most important thing for the cylinder wake for cylinder like induced wake experiment is to use a proper free stream to generate vortex streets for those fishes instead of the fully turbulent boundary layers. So I think the most important thing is the free stream selection. And I think another is to watch the habitat of those fishes to design something that they are interested to let them to swim across or past those areas. Yes, I would say this is very hard and very time consuming to do so, and there's no very well solution for this one, I think.
Okay, thank you. Any questions from the audience? Okay, I actually have like two more questions. So one is like since you do tomo PIV and also planetary PIV, a lot of work especially in the in the like free swimming, we see this whole show like this C-shaped vortex ring coming out like from the 3D in the free swimming. They do showing like a 3D effect do play a significant role in the free swimming in terms of efficiency, in terms force generation performance. In the the C-turn, which is the maneuver, like a very quick and steady motion. Although you mentioned you have not like fully analysis the 3D version of the wake structure, like in the in the C-turn, and you mainly presented like the 2D key features of this in the vortex pair shading from the tail. Can you comment a little bit the 3D wake significance, or whether it's significant, and if so, how significant for the maneuvering part for the compared to the 2D PI, the 2D structure wake for the main flow features.
Okay, so I think the our strategy is we conduct some 3D experiments to observe, to see some important things or information that cannot be obtained from a 2D so because often actually they are vortex rings. So 2D only have the information in the in-plane. So how about the height of the circle? And actually, if the height, I mean, if the circle is flat or is more circular, I mean, I think this the dynamic or kinematics of the wave is totally different. Actually, I read one paper talks about this, and they claim that if the vortex ring is more flattened, which means the fish will obtain a less thrust effect, will suffer with a less thrust effect. So I would say the 3D experiments for the C-term is still necessary because we want to know the highest information for the C-term, whether the fish requires a high thrust in which direction. So this we want to know. And another thing is we conducted some 2D experiments because we want to get some overall the general or say the universal conclusion to the of the relationship between the manifold intensity, the intensity of the manifold and the strength of the vortex. I think they are quite maybe they are quite high, very highly correlated, and I think I'm looking for some people to doing such study because I think there's another very nice saying that like you can imagine the vortex in the wake is similar to the footprint when we walking on the sand. If we run very fast, the footprint is very deep. If we just rock or we just walk, and the footprint is swallow. So when studying the strength of the circulation of the vortex in the wake, we can in turn to infer the condition of the fish. And many researchers have said that in many cases the vortex rain is how to say is the axial symmetry. So you can use the limited 2D information to infer some the overall the generalized conclusion is okay to get. So this is our strategy. And also there's another very important thing is the total PIV data processing is too time consuming here. So we can't wait, and we can do some 2D experiments first to get some quick results.
Yeah. So actually, like I mentioned, I'll keep my next question if there's a time. So actually mention say, hello, great talk, thank you. I may have missed that, but I was wondering if the Reynolds number of the pitching foils you showed was the same or similar to the condition of the live fish. Basically, it's the Reynolds number matching between your pitching foil to your live fish.
So the pigeon foil was also at the order of 10,000, but I don't remember the exact number. So I mainly compare with the Stillhorn number. So I think the Reynolds number is also important. I need to pay more attention because higher Reynolds number may lead to the less coherent wake in the of the pigeon panel. So yes, I think this is a thing that I need to pay attention in the future. Yeah, thank you.
Okay, so if I can just follow up on the 3D and 2D wake pattern. So I agree totally the 2D capture a major a mechanism or the key structure of this shading vortex pairs. And the 3D it is to some degree a signature that whether the ring is more flat or more circle or these I just have this thought that because the vortex ring the shade is also a very strong relationship to the shape of the tail, whether it's a little bit more round or the things. As I'm not promoting that we should trim the zebrafish tail to study the shape of the the vortex 3D vortex, because I do think as you readily mentioned out the 3D format, the vortex ring shape will have a strong impact. I agree very well to the the maneuvering, basically the force generating in the the turning phase. So so maybe we can put a fake tail to some degree, or to study this in the way to to optimize some of the what is this tail looks like, because let's be honest, one of the major stress generating is from this flat tail, which is the atom mass effect or other things. So just as some crazy thought, again, I'm not promoting or encouraging to trim the tail of the fish, because that may be too cruel. So.
Okay, okay, yeah, that's also yeah. Another way, another side is it will be a very difficult experiment to do, because it's very hard to conduct, I think. But I think I agree. I missed the factor of the fin shape. So, but I think.
Well, I just want to say, nevertheless, it's a live fish. It's it's not like robotic tails. There are already some people doing the shape of the tails, to the shape of the foil to see But no matter what, it's a live fish. It's really difficult to from my perspective to do that.
Yeah. Yes. Yeah. Okay.
Okay. Given the time and all the interest, like I saw the peak of the peak time, like there's like 45, 46 people like join the talk. And I want to say thank you very much, like Dr. Han Tu. I'm looking forward to have face-to-face conversation like soon with you in the summer vacation. I see like several of my students is also here. They already text me about like several questions. And anyway, thank you very much. And thanks all the people who staying late or like get up early. And I'll see you next week. Bye-bye.
Okay, see you.